All right, IB seniors, I'm going to show you all integration today, which is the opposite process of finding a derivative. This is a little introduction here to what it's all about. If you have a curve, wacky curve, you want to find the area underneath there. Well, there's not a formula for that. We have all kinds of formulas for trapezoids and rectangles and squares and you name it. There are all kinds of formulas out there for certain geometric figures. But if you have some kind of crazy curve and you want to find out the area underneath there, you can't use any kind of formula. You have to use the process. And that process involves the opposite process of derivatives. So the theory is this here. If you want to get an estimate for the amount of area underneath here, you can build some rectangles here. But that's not going to give you a very accurate estimate of the area because you got some blank space here, here, and here, and here, a little bit of overage over here. So if you made more rectangles and skinnier rectangles, you get a better approximation because you have less wasted space. You're trying to find the area from A to B, by the way. We don't care about what's over here. So there's less wasted space here when we have more thinner rectangles. And over here we have even more rectangles, skinnier still. So the idea is if you really want to be accurate, the most accurate, precise area underneath the curve, why not use an infinite number of infinitesimally small rectangles? That's kind of a new word, infinitesimally. It's hard for me to say even. So the smallest possible rectangles and an infinite number of them will give you the exact area under the curve. And the process for doing that is called the first fundamental theorem of calculus, which is really just dealing with what we call integration. All right, so I'm going to show you a quick example here, and there's some other examples in the folder that you'll look at. To find the area of a curve, which is the whole idea of integration, you're going to use reverse differentiation. You're going to do the opposite process of finding the derivative. So let me show you an example. First, let me show you the theorem. This little funny looking S is very closely related to this E that we have, the sigma. Sigma is for adding up a certain number of rectangles, right? When you have that smooth looking S, you're adding up an infinite number of rectangles. So that's what this means is here. It's kind of like a sigma, but it's for an infinite number of rectangles. And whatever our function is going to go here. And capital F means the antiderivative. And I'll show you how to do that. You got to think in reverse. You know the derivative process, and now you got to think in reverse to get the antiderivative. So you find the antiderivative of your function, and then you plug in the top value and you plug in the bottom value. But let me give you an example here. So they want us to find the area under the curve. So x squared plus 1, we know what that looks like. That's just a basic old parabola. And it starts here at 1. And we know it looks like this here. All right, there's our function. And they want us to find the area from x equals 1 through x equals 4. So there's some area underneath here. I don't know how high up this goes. They want us to find this area here. This might be part of a car. There's kind of a curvy part there, maybe a door part or something. We need to find out how much area is involved there. There's not a formula out there. It's a process we got to find. So think about an infinite number of rectangles. What we're going to do is add up those infinite number of rectangles. We're going to start at 1. We're going to go to 4. And our function is x squared plus 1. Now this here, let me explain what this dx is. Here's your function, which is the height. All right, the function tells you the height as a given value of x. So really we're taking each height is an f of x. Remember f of x means y, right? So the height of this of any rectangle is its y value, its f of x value. The width is what we call dx. It's a very, very tiny, tiny, tiny width. So we have a very small width at dx, and we have a height y. So here's our y, and this tiniest amount here, it's called a differential x. It's the tiniest x imaginable. And again, we're going to have an infinite number of those so skinny, super skinny rectangles. Each rectangle has a tiny, tiny width called dx. So here's width times height. Guess what? That gives you the area of a rectangle, doesn't it? This means you're going to add up all of those rectangles. Width times height. I'll write that on there, and you don't need to write that. every time. There's your height, and there's your width. Together, those multiply to give you the area of one rectangle. We're going to add up all the rectangles, an infinite number, going from 1 to 4. Seems impossible, doesn't it? Here's what you're going to do. You're going to find what we call an antiderivative. The antiderivative of this is thinking in reverse. Normally, we take the exponent and multiply in front and reduce. Well, the last thing done, instead of reducing, first thing we're going to do is we're going to bump up the power. We're going to bump up the power on antiderivative. And then we're going to multiply by the flip of that. So it's the opposite process. You bump up the power and then multiply by the flip of the new power. In other words, you divide by the power. Think about it. If I took the derivative of this here, what would I get? I'd get 3 times 1/3, which would be 1. And then I'd have x squared. I'd get the original term back, wouldn't I? We're going to do the same thing here. This right now is a 0 power. I'm going to bump up the power and make it x to the 1. And then I'm going to divide by 1 over 1, which isn't going to change. So you can see that this is the antiderivative of this. If I took this derivative here, if I took the derivative of this equation here, I would get the original. So to find an antiderivative, bump up the power, multiply by the reciprocal of the new power. Bump up the power, multiply by the reciprocal of the new power. That's called an antiderivative. So that first fundamental theorem I showed you a while ago says if you want to find the area of underneath this here, what you're going to do is take this expression and you're going to evaluate it twice. And you're going to subtract the difference, or find the difference of those two. So you're going to write that down twice. You're going to plug in the 1. Actually, you're plugging the 4 first. It's called your upper limit. And then you're going to plug in your 1 over here. And then you're going to work all that out. It's kind of a mess, but you can do that on your calculator now if you want. Let's just cheat, use your calculator. We just type all this in here. That's 4 to the 3rd. That's going to be 64. So that's 64 over 3 plus 4. Don't need a calculator for that yet. This is not too bad. This is 1/3 plus 1. That's 4/3. And now we need a calculator after all, do we? Let's come on over here. Because we know that's 12/3, right? So we have 64/3 plus 12/3. That's 76/3. Minus 4/3. 72/3. What's 72 divided by 3? That's a perfect number. Isn't that 24? So the area of this here, it's already going here to here is 3, and it goes up rather high. So 3 times, whatever, is going to give you the eventual 24. So this area here, again, this graph goes up pretty steeply here. So you're finding a lot of area, what you're finding here. All of this area underneath this curve adds up to 24. So that's the whole purpose of using integrations, to find the area under a curve. And later on you can find volumes and things like that. So let me pull this back down again. So again, the fundamental theorem of calculus, called the first fund theorem, says that if you add up all the skinny triangles, an infinite number of skinny triangles underneath the curve, then you'll get the actual, precise, exact area of that. So in the process involves finding what's called the antiderivative. We'll talk more about that in the coming days. Just for now, to find an antiderivative, you do 2 things. You bump up the power, multiply by the flip of the new power. All right? Let's do one more real quick without the drawing. Let's say that original function is, let's say x3. 3x3 minus 4x squared plus 2x. And we want to find its capital F. Capital F, we're going to do the opposite process. We're going to bump up the power. It's x3 now. It's now x4. Do I multiply in front? No, I multiply by the flip of that. So I get 1/4 times 3, which is 3/4. I'm going to bump up this power. It's now x3. What's the flip of 3? 1/3. 1/3 times 4 is 4/3. I'm going to bump up the power. The new power is 2. multiply by the flip of the new power. That's 2 1/2 times 2 gives me 1. This is an x0, bump it up, make it x to the 1. That's my antiderivative is what this is called, antiderivative. And you need to find that, and we're not going to do an actual problem here, but you need to find the antiderivative in order to find the area underneath the curve. But double check, look, 4 times this, the 4 would cancel out, you get 3x to the third when you reduce the power. 3 multiplied in front cancels out. And then you have 4x squared, check. 2 multiplied in front will give you 2x, drop the power to 1. So again, to find an antiderivative, bump the power. So the first thing you do is bump up the power, and the second, multiply by, don't divide because then it gets very complicated, multiply by reciprocal of the new power. Multiply by the reciprocal of the new power. Bump up the power, it was a 3, now it's a 4. Take that new power, its reciprocal is 1/4, multiply that in front. That's the process of finding an antiderivative, and if you can find an antiderivative, you can find the area underneath the curve. All right, that's it for now. Look at the stuff that's in this week's folder and see what you can do on these problems.